Okay, I'll make a start now. So, as I said last week, we finished the syllabus. So, content-wise, it has been all delivered. So, these 2 weeks, so this week and the next week, we'll go through the materials again and look at whether there is any gaps in your understanding, concepts, etc. So I need interactions or questions from you or suggestions from you on that respect. Few things like there is a test this Friday, as you know, the final term time test that you will have, again 10%, and it would be based on the rest of the syllabus that we did beyond bending moment and shear force. So from beam deflections and beam stress primarily. So these two parts will be tested. Again, half an hour, 30 minutes at the maximum, and mixture of questions as before. So that would be this Friday. So today what I am going to do is, my plan is to look at few problems from tutorial 7 and then also tutorial 6 if we have, and then also I'll upload the solutions either later today or tomorrow, just to give you a little bit of time to try on your own, and then the solution sheet should be uploaded in Blackboard for you to go through and check the answers and the working, etc. So that's the plan. Other thing is about your group work. So what I'm planning to do is I'm going to publish, I need to look at your timetable and my timetable as well. So I'll email you a couple of Zoom sessions where you can log in and show your work, or if you've got any queries with your group work, for example, so you can raise that. Other option, somebody suggested that if we have got some general tutorial sessions with the GTAs, I'm thinking about that, what will be best way to do that, whether that would be face to face, so 3 or 4 or 5 GTAs are here, you go there and ask them any questions, I will be there of course, or it will be better through Zoom, for example. So you log in, and as soon as one of the GTA is available, you go into so Zoom has got facilities of meeting room, for example. So both of you go into, or 2 of you, 3 of you go into the meeting room and then discuss that. So I'm thinking about that. Maybe it will be one face to face and the others will discuss. So, and if Zoom is successful, then we can do it before your exam as well in January. If you have got anything to discuss, that we can do. Okay, so that's the plan. If you have got any other ideas, anything that you didn't understand, then do let me know, and I can produce a little video, for example. Okay, I didn't get how triangular load in this problem was considered, for example. Then I could probably create a little videos and upload that into Blackboard. So it has to be interactive, and the best place to do that, which I haven't checked in a week, is to raise it through the discussion board. And you can of course email me, but through discussion board is easier, because if you say something and then other people agree to it, then of course I'll make sure that is there. Otherwise it's difficult to know whether it is a genuine problem for you as an individual rather than it's a problem for many. So raise it in the discussion board, that is, I think, in here somewhere. So the discussion board is in there. So raise those issues in the discussion board. Okay. Anything that I have just put, you can create a thread as well. So these two I have created as explain please, or where can I find, that sort of thing. So you can create a thread as well. It's up to you. Okay, so let's start with looking at the examples from the beam deflection. So the first set of problems, it asks you to identify the boundary conditions, because that would be required when we do the beam deflection calculations. So this is asking you what are the boundary conditions in those cases. So first problem is asking, you have got a simply supported beam with a load in the span, and it is asking what is the boundary condition. In each case, take x as the horizontal, so this is the direction of x, and y-axis is vertically downward. So this is the axis system for all the cases. X is acting downward, x is acting from left to right, y is acting vertically downward. Now let's have this as an interactive session. What do you think the first case would be? So the first case is shown as follows. So this is the, so what do you think the boundary condition would be in this case? Go on, suggest something, yeah?
Boundary conditions are determining deflection, both the bending moment and the deflection will be zero, both on equal force.
Yeah.
And
So,
maximum.
yeah.
It will be maximum when they're in the very position below, right?
Yeah, but we don't need all of it. We probably need just two displacement type of boundary condition. But you are absolutely right, bending moment and shear force, if you know them, that they are zero at some point, then that is also known conditions, and we sometimes use them. But in this case, we are looking at where the displacement and rotations are zero. These are the boundary conditions for this type of problem we will require. So do you know any displacement or any rotation in this case? So I'm giving you the clue here that at x equal to 0, which is at the left hand end, displacement is 0 because there is a support. And at x equal to 12 meter, so look at the problems on the other side of the board. At x equal to 12 meter, y equal to 0. So that means the other end it is 0. What do you think would be boundary condition for problem number 2, which is this problem over there on the right hand side on there? What do you think the boundary condition would be? Go on. There will be some questions like this in the test anyway, so might as well say it. What are the known boundary conditions? Any displacement or slope that you know? Yeah. At x equal to 0, y equal to 0, absolutely. And at x equal to a, y equal to 0. Yeah? So make sure that you get these ones. What about the third one? Again, x should start from this end and y is vertically downward at the left hand end. So what are the known displacement or slope that you know? Yeah?
And x is equal to 0, y is equal to 0.
That's good. At x equal to 0, that means at the support, displacement is 0 or deflection is 0. What are any other things?
X is equal to 7, but that's going to be the location. There is x is equal to the distance between 0 and w, which is at w there will be the highest deflection.
Not sure. What about at the free end? If it deflects, it will continue to deflect.
Oh wait, the highest deflection is at the free end.
Yeah. So, but we don't know that value, so we cannot take it as a known thing.
We can easily find that value using the
No, when you do the integrations, you will come up with an integrating constant, so you don't know the value. Yeah, okay. Yeah, absolutely. At the left hand end and the support, the slope or the rotation is 0. Yes, absolutely. dy dx is 0. That's right. So at x equal to 0, y equal to 0, as you said, and as you have rightly said, at x equal to 0, dy dx, which is the rotation or slope, that is 0. Absolutely right. So a fixed end or a built-in end will have rotation 0. So known condition. So having a maximum quantity would not make sense unless you find out what is that maximum value. So you need to have the known value as the boundary conditions. Yeah? And boundary conditions here we are talking about in terms of the displacement or rotations, because that's what we are finding in the deflection equation. Bending moment shear force you may know. For example, this problem on the right hand side, free end, bending moment is 0, shear force is 0, because that's a free end. It cannot have any bending moment shear force there. And also you know the left hand side it would probably have the bending moment maximum. But this doesn't help you when you are when you are trying to find out the integrating constant from the deflections equations. So go for known places where you know the deflections or where you know the rotation. These two are the things that you need to look at in these problems. Okay, what about problem 4, which is in there? Okay, anybody wants to go first for this problem? This right hand side problem? Yeah, go on.
At x equal to 0, y is equal to 0.
Yeah, we know that at x equal to 0, y equal to 0, deflection is 0. Very good.
At x equal to 10, y is equal to 0.
Why y equal to 0? Because it said support displacement is 0.05 meter.
But there is a
So due to the load, the support has sunk so much distance.
oh, okay. So due to the support. Okay, so at d1, so at y is equal, so at x equal to 10, y is equal to 0.05.
Y equal to 0.05. So that would be the answer. Yeah, at x equal to 10, y equal to 0.05. So any known things that you can find out from the figure, that would be your thingy. Okay, very similar. Again, the problem number 7, which is very similar to the previous one. But what do you think this time the boundary condition would be? You said the first one last time.
Also, there's a second one that I feel like wanting to try.
Yeah?
The second boundary condition definitely has something to do with trigonometry. So 3 isn't the, so let's say that 3 is the horizontal of a right angled triangle. So 3 is the, okay, so
Okay, think about it. You raised your hand. At x equal to 0, dy dx equal to 0. Dy dx is 5 degree. Okay? Anybody else? This side is not contributing. Okay? We want your contributions. Anybody from the right hand side? Are you getting it though? Once the solutions are given. Yeah? Okay. Negative in that direction, but absolute value is 5 degree. Anybody from that side? No? So what are the known boundary condition in this case? Now of course as before, at x equal to 0, y equal to 0. That means there is no deflection due to fixed end. But what about any other conditions? Now at x equal to 0, also we know the rotations. Now the rotation dy dx is 5 times 5 degree. So you need to convert that into radian really, because the slope, what you get from those differential equation is in radian. So that dy dx is 0.087 in terms of angle of rotation or slope at the at the left hand end. Okay. What about problem 6? How many boundary conditions you know in problem 6? Okay, I want some answer. First one from this side. Okay. Anybody from this side, give me a boundary condition. What do you know in terms of the deflection or rotations by looking at the support structures or the loading or the beam? What do you know in terms of the deflection or rotations? Okay, somebody from this side, okay? At x equal to 0, at the support y equal to 0. Very good. Now I go to the other side. You give me another one, okay? X equal to L, y equal to 0 because there is a fixed support. Okay. Middle group. Do you have anything else? Yeah?
dy by dx is 0 at x.
Okay. dy dx equal to 0 at x equal to 0. So these are the three boundary conditions. So you know now how to deal with that. And these are absolutely essential to find out the deflections equations and those things. Okay, so if you know that, we are going to do some problem. So the first one is calculate so problem number 2 is given a simply supported beam and it is asking the calculate the bending moment distribution. Identify the boundary condition. What do you think the boundary conditions for this one would be? At x equal to 0, y equal to 0 and x equal to 5, y is equal to 0. Then obtain an expression for the deflection at all parts of the beam by integrating the moment curvature relationship and calculate the maximum deflection. Now some bending moment results may be available from earlier tutorials. Some questions will require the use of Macquarie brackets or fictitious additional loads or simply some clever tricks. So let's look at problem number 1, let's say. So problem number 1 is this beam. Okay. So 2 kilonewton per meter over 5 meter distance. So that's the beam. So and it is asking us to find out the bending moment distribution. Now there is only one load, so it is easy relatively. So we don't have to do, so I take a section at a distance x and find out what would be the bending moment distribution. Now we know there is this 2 kilonewton per meter load. To calculate the bending moment distribution, I need to find out what are the support reactions. So to get the support reactions, we can do a free body diagram and find the support reaction. So the total load is 10 kilonewton. So 2 kilonewton per meter over 5 meter. Total load is 10 kilonewton. And it's a symmetric beam. So half of it will go to over the left hand support, other half over the right hand support. So 5 kilonewton each. Now it is relatively easy for me to find out the free body diagram, and we take again x is going from left to right and y vertically downwards. So if I take a cut or free body diagram, at a distance x from the left. So if I take a cut at a distance x from the left, say this distance is x and that is 5 kilonewton, and then my shear force and bending moment diagram as shown. Do remember the sign convention that we use or using mostly in this case. So this is an element on the left and right, and this is a positive sign convention would mean that I will have a load going downward, shear force going down on the left up on the right, and bending moment we will assume is a hogging bending moment is positive. So these are the positive sign convention that we are using. Now, if so, that means on the right hand side I put this shear force going up. So that's the right of the cross section and bending moment in this way. And then I draw the equilibrium equations for this case. So this moment, now whenever we are doing the, as I said repeatedly, whenever I am doing the equilibrium equations, then I can use clockwise or anti-clockwise possibly. So when you do the equilibrium equation, summation of moment 0, then this sign convention does not follow, because this is left or right, it's related to only to the bending moment, which is internal stress. So the internal stress would have some form of uh, um, sign convention like this, which is different what we do in terms of the summation of all the moments are 0 or not. So this moment M is clockwise, so that I am using a plus sign M. Moment due to the reaction force or the left hand support is, I am taking moment about this point, so I hold my bar like that. And how this 5 kilonewton is rotating my bar? So consider the pivot point where you are taking your displacement. This is my pivot point, moment. This is my pivot point, because that's where I am taking the displacement, the moment equilibrium. So 5 kilonewton load will rotate my beam in this direction. So as if it is going in a clockwise fashion. So, and what is the moment amount? 5 times x, the force times the distance. So that's why with the plus sign, because it is clockwise moment. What about this 2 kilonewton per meter load? So what is the total load? Total load is 2 kilonewton per meter over a distance x. So the total load is 2 times x. So that's the total load. Total load is 2 times x. And where does it act? This is an uniformly distributed load, so that will act at half a distance from this side, middle of this side. So the distance of that load, so if you say this is my 2 times x, and that will act at a distance x over 2. So this is the distance x over 2. Now which direction it rotates the beam? Now the pivot point is still there, and this load will rotate the beam in this direction. So this is anti-clockwise. So that's why this negative sign. So if you do that, then you get m is equal to x square minus 5x. So that means these expressions will give the value of moment at any distance x. Give a quick sense check. So if you put x equal to 0, so if you put x equal to 0, so at x equal to 0, so mx is equal to 0 minus 0 is 0. So that makes sense, because this is a hinge point, so moment is 0. And also you know moment is 0 at the other point, because there is also a hinge point. So if you put x equal to 5, for example, then that will be 5 square minus 5 times 5. So that it means mx equal to 0. So the doing a bit of a sense check makes whether your expressions is right or not. So you can look at the structure and you could say that this is the right one. Now before going further, if you have been asked to do a shear force expression, how do you do that? So you know this is the shear force V. You can take, and then you can take an equilibrium equations for this shear force. So let's say positive force upward is positive. Let's say because we are doing the equilibrium, so you have to do that. So this is equilibrium of this element we are doing. Thank you. Thank you. So 5 kilonewton is going upward. So I put that as plus 5. 2 kilonewton per meter is going downward. And what is the total load? 2 times x. So minus twice x. And V is going upward. And these are the three forces in this case. So that is equal to 0. So V at a distance x. So if you write it down in a neat way, Vx would be 2x minus 5. So if you do a sense check, so at x equal to 0, Vx will be equal to minus 5. That means over left hand support, your shear force would be minus 5, and at x equal to 5 meter, Vx would be plus 5 kilonewton. So that means, and at x equal to 2.5, for example, half the span, Vx will be equal to 0. So that means at the mid span, shear force is 0. So this is the expression of shear force. I may ask you to find out expression of shear force as well. So this is an expression of shear force at a distance x. But this is not required to calculate deflection. So this could be just an expression for you to find out. Okay. So how do we solve this problem? Now the second problem that we have been asked was to calculate the boundary condition. So the boundary conditions are at x equal to 0, y is 0, x equal to 5, y equal to 0. Third is obtain an expression for the deflection. So EI d2y dx2 is m. And what is the value of m? M is, general expression is x square minus 5x. So we put m as x square minus 5x as this. And we start integrating. So integrating with respect to x, we get EI dy dx is x cube over 3 if you integrate x square, minus 5 times if you integrate x square over 2, plus c1. c1 is an integrating constant, for example, which we don't know yet. Integrate with respect to x once again, you will get this expression EI y x to the power 4 over 12 minus 5 over 6x cube c1x plus c2, where c1 and c2 are the integrating constant. How do I find c1 and c2? I find c1 and c2 from these two known boundary conditions that I wrote at the top. So I use the first one at x equal to 0, y equal to 0. So I put that value here. So 0 is equal to 0, 0, 0, etc. So that will give me c2 equal to 0. I use the second boundary condition then, x equal to 5, y equal to 0. Then that gives me value of c1. So once I know c1 and c2, I write down my expressions of deflection. So that is what has been asked, that obtain an expression for the deflection of all parts of the beam by integrating these moment constant. So this expression y is 1 over EI x to the power 4 over 12 minus 5 6x cube plus 5 cube over 12x is how the beam would deflect. So the beam is likely to deflect in this manner, for example like this. So this is the deflected shape. So this is the deflected shape. So this deflected shape is, you can find by using this equation. So you can see if you put x equal to 0, then you find at y would be 0. Similarly, if you put x equal to 5, you should get y equal to 0, because that's how you have found c1 and c2. And you can find the maximum one. And by drawing the diagram, you find that maximum is at the midpoint, at the midspan. So you put x equal to 2.5, for example, which is the midspan, and that will give you the maximum deflection. So if you want to find out that part 4 where the maximum deflection would be. So maximum deflection, so at the location of maximum deflection, the slope will be 0. Now, of course, in this case, you could use the symmetry and say, okay, midpoint it is maximum, but maximum deflection usually would be related to the slope is 0. So, at the location of maximum deflection, the slope will be 0. Of course, you can use symmetry here and conclude that the maximum deflections will be at the midspan, i.e. x equal to 2.5 meter. So we can check that because we do have the equation of the slope. So this is the equation of the slope, ei dy dx is x cube over 3, etc. So put values of x is 2.5 meter. Put values of x equal to 2.5 meter and see whether that is exactly 0 or not, and you will see that it is indeed 0. So at the midpoint, the slope is indeed 0. So at the midpoint slope is 0. So if the location of 0 slope is not obvious, say the load was, so you cannot use any symmetry or anything else, then you need to solve this equation in terms of x. So you put that equal to 0 and find the locations of x where the maximum deflection would be. So once you know the location, then put the values of this and then you get the y max. So in this case, you say the y max is 0.814 millimeter. Now you need the value of EI, which is given for this problem. EI is 20 mega Newton per meter square. So you are getting a deflection, maximum deflection is about a millimeter. Yeah, go on.
The reactive force is acting all along the depth, or is it just acting along the midplane?
What reactive force?
The reaction force provided by the hits.
So that's over only the support.
Yes. So is it acting all along the depth or only at the midplane of the?
Oh, the reaction force. To calculate the shear force, that's slightly involved questions. Okay, it is acting over the whole depth for the time being. Okay, so not just the midplane, whole depth. But how that vary, so that implication of that would be to alter the shear force distribution or shear stress distribution. But as a shear force over the whole cross section. Okay, so the reaction force at the each end will act over the whole cross section. Okay. But how that will vary over the depth is tricky questions. You will do that in your second year. Okay. So it is not uniformly varying over the depth. Okay, so you can see the deflection is 0.8 millimeter. Now just to put in a context of it, so deflection, you can see that the assumptions that we take, that it is a small deflections problem. So the way I have drawn it here, this is not to the scale, of course, because the span is 5 meter and the deflection is 1 millimeter. So that is very small deflection, and 2 kilonewton per meter is not a small load. So 2 kilonewton is approximately 200 kilogram of mass per meter length. So for example, two people standing half a meter apart, each one weighing 100 kilogram, for example. So that's a load. Yes.
I've got a question. I've had this thing squeaking in my mind for days. EI's value. Prove me wrong here. Do you think we should convert EI to kilopascals first before putting it in?
No, you use any unit that is consistent. So the load is in kilonewton and length is in meter. So I used in this case meganewton per meter square to kilonewton meter square in this problem. In this problem I did. So if you, other option is to convert everything in Newton and meter, for example, or Newton and millimeter. but use consistently the same unit for everything. Okay? So in this case, as the problem is given in kilonewton, load in kilonewton and length in meter, I converted EI to kilonewton meter square.
So if the beam is, in this case, we are not considering the self weight of the beam.
No.
Now, if,
So the weight, self weight is possibly taken within that 2 kilonewton per meter.
so if there is no uniformly distributed load and we have to consider only the self weight, can we consider self weight as a UDL?
Yeah, absolutely. So the self weight could be included, taken as an UDL, and of course you know then your inherent assumption is that the cross section do not vary along the length, or it's a prismatic beam, because if that varied, then of course the self weight will also vary. It won't be uniformly distributed. Any other questions on this problem? No? Okay. Good. So that was problem number 1. What about problem number 2? Problem number 2 is this problem B here. Why that is given in terms of A? Okay. So no value is given, but that is done in terms of A. Okay. So it's not to worry. So this is the problem that is given. So the first thing it asks us to find the bending moment distribution, calculate the bending moment distribution. So what do? We first need to find out any unknown support reactions. So that's the first thing. So draw the free body diagram of the whole beam and find the support reactions. So if you draw the free body diagram of the whole beam, then you will have an unknown reaction force at the support and an unknown moment. Now if you do the equilibrium of that, then of course the summation of vertical force will show that the reaction force going up is W as well, and the moment, support moment would be W times A. Why is that? Because the load at the free end is going to create a clockwise moment W times A. That must be balanced by the support. So the support moment must act in the opposite direction, which is anti-clockwise, and must be W times A. Now you probably haven't done many of these cantilever problems, so make sure that you familiarize yourself and do some more problems. So first year problems, mostly you will get either the simply supported type or the cantilever type, and in some cases you can get some overhang or either way, but you wouldn't get any statically indeterminate type of structure. So these are the primarily two types of structure. So make sure that you are familiar with both of these sets, a simply supported or a variation of it, or a cantilever. Now cantilever could be a vertical cantilever as well as a horizontal cantilever.
Wait, so the shear force diagram for this, if we're going to take a cut at x where x is less than a, the shear force diagram is going to be v plus w. So v.
Okay, so why don't we do the shear force diagram?
Yes.
So let's say I take a cut at a distance x, let's say something like this. So if I do a cut at a distance something like this, then I have got a shear force V going like this, and a moment, as soon as I made a cut, then a moment is going in this way. So what is the shear force? Now the shear force is vertical force equilibrium. So W is upward, so that is W is going up, and shear force according to my sign convention, that is also upward. So W plus V at x equal to 0. So that gives me Vx is equal to minus W. So that is my shear force expression. So it will start with a negative value at x equal to 0, and it will continue. So the shear force would be minus W for the whole beam, because this does not depend on any x value. So shear force for this beam would be continuous at the same value with W and negative W, like that. So this is the shear force diagram. Okay? Now what about the moment diagram? So consider a virtual cut at a distance x from left. Use free body diagram. You can do either left side or right side. So this is what I have shown it here. If you do either way, if you do the left equilibrium or the right equilibrium. Let's say you do the left side equilibrium analysis. So what it means that you are only considering this side, for example. So this side if you are doing in this way. So only that bit you are considering. So if you do that, then you have got a moment going clockwise, so m, w time x, it is going in this direction, so that is clockwise, and w time a at the support in the negative way, so minus wa equal to 0. What you will find in first year structures is really you need to grasp very well two things to do any of the problems. One is the idea to draw the free body diagram. So if you make a cut, if you replace the support, physical support, with an equivalent force that it may come up, so the idea of the free body is absolutely important. So grasp that concept by several ways, by looking through the problems, reading a book, or trying to resolve some problem, unknown problem. For example, analyzing this pedestal, for example. So try to draw and think about the free body diagram. That's the first thing you need to do. And second thing is applying the equilibrium equation. Summation of horizontal forces 0, vertical forces 0, or the moment of all the forces and the moment 0. These two things, concept, if it is clear, there is no problem in the first year structure. Just these two concepts. How to draw the free body and what is free body diagram. And second thing is this equilibrium equation. This is all the things, everything that you need to know in first year structures. And we haven't done anything more than that in this whole 10 weeks so far. We have used this concept again and again for the whole structure, to the little bit of structure, to some bigger part of the structure, just these two concept consistently from one to another. Free body diagram and equilibrium equations. Okay? So make sure that you do that. So then moment is at a distance m, x is wa times wx. So if you take w outside, w times a minus x. Now what about the right hand side? If you took the right hand side free body, then of course the support is not there. Now if m goes that way, so this is the left side of this cross section. So the shear force should go down and moment should go at that way. So moment is in this direction. So if you take moment about this point, then you have got m, which is anti-clockwise, so minus m, and then moment due to w, so w times a minus x. So this also gives you the same expressions, that the moment is equal to w times a minus x. So it really doesn't matter which side you take the moment, you take the free body diagram, whether you take the left hand side of the beam or the right hand side of the beam. Now of course in this case, right hand side of the beam would have taken little bit of advantage, yes, because you have got only for the moment two forces to consider, w and m, whereas here you need to consider w times a. It is also useful because you didn't need to consider the free body diagram of the whole beam. You didn't need to find out what is the moment at the support. If you consider only the right hand side, you really didn't need to consider this second step. You really didn't need to consider this second step, what was there. You didn't need to consider that step. if you only consider the right hand side of this one, then you didn't need to consider the second step of this case. So sometimes doing an equilibrium of the left or right depends one side being advantageous than the other. So in this case, just doing the right hand side would have made you not to consider the second step to calculate the forces and on the support. So if you do the right side of the free body diagram. Now, the rest of the steps are very similar. So what you do, you equate that EI d2y dx2 equal to m. So if you do EI d2y dx2 is equal to m, then m is w times a minus x, w times a minus x, and then you integrate with respect to x, you get this expression with integrating constant c1, you integrate with respect to x again, you get that expression eiy. And then you go back and put in those two values of x equal to 0, y equal to 0, x equal to 0, dy dx equal to 0. That would give you c1 and c2. So how do you get that? Now, of course, you can get those two by putting in the values of x and y in here. So these expressions now is if you put x equal to 0, y equal to 0, you'll get c2 equal to 0. And if you put x equal to 0, dy dx is 0, then you'll get c1 will also be 0. So putting back the values of c1 and c2, y is this expression, that's the expression of the deflection, and this is the expression of the rotation. Okay, so that completes part 3. What about part 4? Maximum deflection. Now, in this case, you may say, okay, the beam is in this way and the load is in that, so my deflection is going to be something possibly like this. So I am expecting my maximum deflection would be at the free end. So that would be delta max. Okay? So that will be delta max. Remember in the previous case, what did I say? Previous case, I said, in this case, the maximum deflection will occur where the slope is 0. In this case. Is this true now? No. The slope is 0 here. Deflection is 0 there. Deflection is maximum at this point, free end, where the slope is not 0. So did I say something wrong here? That is clearly the case. The slope is 0, deflection is maximum. What happens when I went to cantilever case? So, okay, I'll ask you to think about now. Let's say we know maximum deflection is at x equal to a. So at x equal to a, maximum deflection will occur. So you put the values of y x equal to a in this expression. So a times x equal to a, you put that in, a square over 2, a cube over 6. So y max is w times a cube over 3 ei. This is an important expression because in many cases you will get a problem which is of cantilever type, or also you can convert any other beam to an sort of part of the beam, for example, as an equivalent cantilever. So if you can, although in real situations you will have this as a data table, you don't need to remember as such, but if you can remember, this is an useful expression to remember, that maximum deflection of a cantilever beam is the load at the tip times a cube, which is the span in this case to the cube, over 3ei. Now this is the question, as I said. Also note that the slope at x equal to a is not 0, which is referring to the previous example of the simply supported beam. In fact, the slope will be maximum at x equal to a. So that you can see the slope is maximum at this point. Question is why? Think about it. Okay, we have run out of time now. So I'm not going to give you answers on to this one today. So why these things are different for simply supported to cantilever? Thank you. So I'll see you on Thursday then. So this is the question.
I had a doubt on this structure.
Yeah.
Here, this entire structure is supported by this thread, and the tension due to the thread is acting only along the mid plane.
Do the free body of the two parts, then it will be clear. Just do the free body diagram of two
So,
parts.
if while drawing the bending moment diagram, should I consider only the middle part or the entire bit?
Sorry, I didn't get that.
While drawing the SFD or BMD, should I consider only the mid plane or the entire beam, because the tension is acting only along the mid plane? So,
No, tension would be, so this will create a bending moment along the whole beam length.
so we
So
can
it
do
is
this
like
normally.
a cantilever. Yeah, absolutely. You need to consider the whole thing.
For the test this Friday, is
Yeah.
it on lecture notes 4 and 5 and
So it will be on stress,
yeah,
beam deflection, and also the second moment of area. So 5, 6, and 7.
5, 6 and 7?
Yeah.
That's the tutorial sheet 5, 6 and 7.
Tutorial sheet 5, 6, and 7. Also lecture notes probably also 5, 6, and 7, isn't it?
There's something on thermal capacity.
Yeah, that will be there as
That
well.
will be there.
Yeah.
I don't understand with this question. Why is M negative here if the sign
So-
convention
so-
says
so-
that it's
so-
positive?
Yeah, so that's the sign convention for bending moment, which is the internal one, and this is where we are doing the equilibrium. So when you do equilibrium of the whole part of the structure, the part of the structure, you should use either the positive as a clockwise or anti-clockwise angle of that.
Okay.
Same is for shear force. This could be pairing force, but when you are considering equilibrium as a force, either vertically upward force or vertically downward force. Yeah.
I asked you last Thursday about this, the course work,
Yeah.
and you said that I had to, because for the bed moment diagram, I had to treat it as two loads down,
Yeah.
and then a uniform across the middle.
Yeah.
I've searched a lot of places, I've searched a lot of beacon, and there's no value for a load for me to this.
You know the total load, isn't it?
Yeah.
So if you know the total load, so you can think about what would be these due to these two loads, for example, these two hump in that way.
I can't get values. But what we know is, so that the total, what is it?
If you don't have that from any information, take some assumption. Exactly.
Right, the assumption we need is so the centre of mass acts towards this end.
Yeah.
So just around here, so can I assume that that's 2/3 along and treat it as a triangle? The whole thing as a triangle?
Why do you need a triangular? You could have a uniformly